Done.
They're done. They were due tonight. Yeah, that's right. And I think a new homework is going to come out today, and the next project is coming out. When's the next project coming out, Pat? Thursday? Thursday, yeah. And that's the last project. We are almost done with the course. It's kind of hard to believe. So now we're going to enter into the sort of fourth major section of the course, which is making lots of decisions. So we sort of started out talking about search, and then we talked about modeling uncertainty, and then we sort of applied that in our machine learning, foray to think about how to make single decisions. If you're trying to decide whether something's spam or not spam, or you're trying to decide whether this picture contains a person or not. And then it's just sort of, this is the input, and the output is a single decision. So now we're going to try to put it all together in a way where we can show an agent making a sequence of decisions over time. So the way that we're going to formalize this is with something called a Markov decision process. So today's class is going to talk about MDPs, and people say MDPs instead of the whole thing, and also partially observable Markov decision processes, which are going to connect back to the Bayes filter and the particle filter work that we were doing. And then it's going to set us up in the next couple of classes to talk about reinforcement learning. So reinforcement learning is a generalization of machine learning where instead of just making one decision, you get to make multiple decisions over time. And that can make your life harder in some ways because you have this history, right? So history is hard, right? It's complicated, and you have to somehow figure out how to incorporate what's happened to you in the past in order to make better decisions in the future. So it's hard because lots of things could have happened in the past, and there's this sort of data bottleneck, but it's also an opportunity because it's not like all or nothing. You can make the wrong decision now, but you get to try again tomorrow and make a better decision tomorrow. And what we're going to talk about is sort of putting it all together and how people think about that. So any questions about anything so far? Okay. All right, so MDPs. So this actually comes all the way back to the beginning when we were talking about ways of formulating a problem. So we were talking about the state, the set of actions, the transition model of what happens when you take an action in a particular state, a goal test, and maybe a path cost. Or people talk about cost and talk about rewards. So a cost is bad, a reward is good. You can have negative rewards, and that's like a cost. So an MDP is in this realm of problems. But what we're going to think about is what happens when this transition model is no longer deterministic. So what does that mean? We talked about this a little bit already. When our transition model isn't deterministic.
If you know your state and your action, you don't actually know exactly what state you'll end up in.
Yeah, exactly. You don't know for sure what state you're going to end up if you take a particular action. And yet you have to take an action anyway. So you know, in an MDP, we're going to know the transition model. That means we're going to know a distribution over the next state if we take a particular action. But we're not going to know for sure what state we're going to get in. So this is like a robot maybe, and it's got gear slip. So if I try to drive forward 1 foot, maybe I'll succeed, but maybe I'll only drive forward half a foot because my motors are slipping. Or maybe I'm trying to convince a person to do something for me. So I could say something, please open the door for me, and maybe that'll work. Maybe the person actually will open the door, or maybe that'll fail. Maybe the person doesn't feel like helping the robot today. And so I could take that action, and they just could walk away from me because they're not going to try to help me. So to sort of formalize this, we're going to have, same as before, a set of states. And then we're going to have, also same as before, a set of actions. But our transition function is a probability distribution. So we're writing this as a pi of S. So it takes as input a state and an action, and it returns a distribution over successor states. So this distribution here is basically the probability of, I should write it as a probability maybe. It's a probability of S prime given that I was in state S and I took action A. So transition of S and A is some distribution over S. This is just a way of saying it's a distribution over states. What it equals is probability of S prime, my new state, given my current state and my action. So this has to sum to 1 over all the states. It could be 0. So it might be like there's a locale, just like we were talking about with search, there's like might be a locality constraint. I might know if I'm a robot and I'm here and I only turn my motors on for a minute, there's a limit to how far away I could possibly be, even if I sent completely random control signals. So that might mean that a bunch of these probabilities for states that are far away are 0, but for states close by, there might be some probability here. So I have this non-deterministic transition function. And then I also have a reward function. So this is sort of what your goal test looks like in MDP land. So you could use this to represent our sort of goal tests that were predicates by having 0 reward for, and 0s and 1s basically for whenever you reach the place where your predicate passes. But you can also have more flexibility. So you can assign, some places might be okay and some places might be really, really, really awesome. And you can represent this in the reward function. And the way that people give these reward functions to these algorithms is they make them up. And it's something that gives that gives a lot of us, we just feel weird about it. Because as we'll see in class today, if we give different reward functions, we can get dramatically different policies out. We'll have an optimal agent will act dramatically differently depending on the reward function. So a lot of current work in this field right now is about where do we get these reward functions from. So there's something called inverse reinforcement learning that says, well, I'm going to watch people play this game or act in this world and then try to induce the reward function. And then once I know the reward function, I can just solve the MDP and try to act optimally. There's some work trying to learn the reward functions in kind of an animal training paradigm where you have a person with like a clicker or something. You've ever seen clicker training of an animal? Like you click every time they do something good. So you're having the person give the algorithm these kind of clicks to say when it's doing the right thing, and then try to figure out from that what these reward numbers should actually be. But for the problems we're going to talk about today, we're just going to make them up and try to encode our preferences in this reward function. You guys saw how this was also true in the machine learning work that we were doing. So like you could estimate with the spam filter, you could estimate the probability that something was spam versus not spam, but that didn't necessarily tell you whether or not you should show this email or erase this email for a particular person. That depends on the value, the cost or the reward of false positives versus false negatives versus true positives versus true negatives. And those are dependent on the situation and dependent on the particular person using the system. So similarly, this is sort of what the reward function can come from. Okay, so this is sort of showing an example of one domain where we're using MDPs. This is for my research. I think I've shown this video before, maybe, of a little guy playing Minecraft. And the way it works is the state space is the location. I'll play it again so you can see him doing it again. He's in the corner here. The state space is all the locations that little guy could be, crossed with all the locations that one block could be. So there's lots of different possible states. The action space is moving in any of the 4 cardinal directions, as well as placing a block in any of the 4 cardinal directions. And the goal is to get to this, let me play it again, is to get to this purple square over there as quickly as it can. And there's some noise. So if you try to move, you might not succeed in moving exactly where you think you are. So you might like slip into the trench or something else like that. Yes?
Wait, why is there noise and why is this not deterministic?
Yeah, we could, so it is a simulation, so we could make it deterministic. It turns out that it's actually really not deterministic for kind of a silly reason, which is that the control API that we're using to actually talk to Minecraft uses JavaScript. And the way that it works is we it's basically directly simulating key presses. So like if I want my guy to move forward, I have to push down programmatically push down the forward arrow key for a defined period of time and then lift it up. So there actually is uncertainty once we discretize the world into our state space. And we're okay with that. We like that because we wanted this to be a world that would model some of our robotics problems where the same thing is true. Like there's uncertainty in how our robots are actually going to move through the world. So this is sort of one example of an MDP problem. And this is another one. This is from the book. It's a lot of people use these grid worlds to model MDPs. So here, I'm a little guy. I'm trying to wander around in this maze. This is an obstacle that I can't go in, and I get +1 reward if I end up at this state, and I get -1 reward if I end up in the pit of lava or whatever that might be. And here they say there's noisy transition dynamics. So if I move forward, I can't move backwards. I can move forwards, left or right. And if I do forward, the intended action happens with probability 0.8, and with probability 0.2, I go off in some other direction. I go either left or right instead of forwards. So, and the goal is basically to try to figure out what to do to earn the most reward over time. And that is called solving the MDP, and we'll talk about how to do that in the next part of the lecture. But before we do that, though, I wanted to have you guys go through this exercise of defining your own MDP, and so maybe you guys can sort of turn to your partners and come up with some problem. It doesn't have to be a grid world. It can be something else. So people talk about sometimes like somebody interacting with a cell phone, or there's control problems like an inverted pendulum, and you're trying to keep something balanced. There's a word for keeping it balanced, and uncertainty, and sort of how the state evolves. Yes?
I have a question about the reward thing. Is the reward
Yeah.
when you enter the state, or is it like if you terminate in that state?
Yeah, people do both. So, and you can make the math work either way. So it can be just for being in that state. So like however you got there, once you enter that state, you get a cookie. And it can also be for being in that state and then taking an action. And then you get a cookie for taking the right action in that state. Does that make sense? The math works out either way. It's just sort of different where like where the summations, how the summations go and where things get pulled out. And it's I haven't figured out if there's a a good reason to do one versus the other, but people do it both ways. You just have to be consistent about it. All right, so why don't you guys turn to your partner, somebody sitting next to you, and then spend a couple of minutes coming up with your own MDP, formalize some problem as an MDP, and then we'll come back together and talk about it.
Facebook, you wanted to sort of- Or it's probably like, or at this point you have statistics. Usually what people click on and how far they scroll.
Yeah, you could also just do like page
There's a lot of fun metrics which we use to get us from like this one you probably know like when you put it on your feature what you're doing for the feature, you probably don't want to pass
But the problem is with back. What?
Okay, you guys ready to come back? A couple more seconds. Okay, who wants to share with the class? What your MDP is? Yeah.
Have a robot with noise taking notes in a class.
Say it again. A robot taking notes in class.
Yeah.
Okay. And what's it trying to take notes of? So what's the states?
What is written down.
Okay.
And
Notebooks? Or like it's on its hard drive or something?
either way,
Okay. And what are the actions?
drawing letters.
Okay. And And what are the transition dynamics?
So presumably there's some noise, so if it tries to draw like a P, it might end up drawing an A.
Mhm.
Or,
So like probability of a typo or something. So we can kind of imagine like it's typing at its keyboard or something, and there's some probability that some particle is going to come down and make it type the wrong thing or something like that. Okay, or just, you know, it's actually pushing buttons and it could push the wrong thing. So you might actually imagine enriching that and saying like, well, it's a QWERTY keyboard, and so there's some error of a displaced by one letter offset. Okay, and what is the reward function?
how well it matches what it's trying to take notes on.
How well it matches what it's trying. So how does it know that? Like we
We tell it.
we tell it. So we have it. Okay. So how well? Maybe like the edit distance from
Yeah.
ground truth. Okay. Edit distance. Distance from ground truth. So what I might actually do instead is refine that a little bit and make it say that its goal. So what a lot of people will do with these reward functions is, instead of sort of having it be a directly measuring the edit distance, you might say that like I'm gonna at the end say that I'm done. And that might be one of the actions. And then at that time, my reward is the edit distance from ground truth. And before that, my reward is -1 or something like that for every step that I take. And what that does is gives it an incentive to get to the goal as fast as it can. Does that make sense? Okay. And then basically and then there might be a way to do backspace as well, so it can like correct itself. And then it basically has to decide at every time step whether it should erase what it just typed or type a new character in order to get to the what it's supposed to be typing as fast as it can. Cool. What else? Let's give another one.
It could be like modeling a user navigating through your website, trying
Mhm.
to get to a feature.
So user navigating website. So what are the states?
Like the page or like the stuff that's displayed.
The
Actions,
page.
like link clicking.
You're on, the action is link clicking. And
Transitions, like the probability that they click on a link or like they go or will see something or stuff, so you can get that all from metrics.
so the probability that they click on the link, or the probability that that link takes them where they want to go? Because if the actions are clicking on a link, then they, like, you get to know what link they clicked on, right? Like if that's what the action is. If you, does that make
I
sense?
was modeling where users ended up.
Where you, okay, so like, so then you might be, so what does the agent get to decide? So you might decide like what, like maybe you're like /dot or something and you have all these different articles
Oh yeah, which one?
and you get to decide which ones to show. So that would be,
Right, or where to
okay.
show it.
Yeah, where to show it, how to lay out. So what you're trying to do is, what do people call this?
Engagement?
No, there's that A/B testing, where they show different versions of the website and try to see which one gets the person to do what the website designer wants the person to do. So let's say page layout. And what you'll do is discretize this. So you'll have to actually enumerate all the different page layouts in the sort of naive formulation of these problems. And all the ones we're going to talk about, we're just going to enumerate all the states and all the actions. And then the transition model is the probability of the new page given the page layout, given the existing page. And like you said, you could get that from metrics, so you could observe what people are doing. And actually, like you're sort of pushing towards the RL problem, the reinforcement learning problem. So like it's actually pretty hard for us to just write down the transition model. Like maybe we could in Minecraft, because we studied how the JavaScript Minecraft API works, and we can kind of make up some numbers, or just estimate empirically what the transition dynamics actually are. Or here they're just making them up. But in this, it might be hard to make up realistic numbers, and you might actually need to do reinforcement learning to get this from data. One of my good friends from MIT who works in RL actually started a job at Amazon, and he was also considering Yahoo because they were interested in exactly this kind of problem. Like, how can we learn how to place our ads to get people to click on them more effectively? So what's the reward function?
The user doing, or like it's
Yeah.
happening.
User doing what you want. Clicking the link that you want to click on, or maybe buying the product at the end of the day that you're trying to sell. Okay. All right. Anybody else want to share, or should we go on? It's okay. All right, we also put a problem like this in the homework, so there'll be a discussion question, so you can do it with more time to think in a venue where you can write it down. Okay, so if this was a deterministic world, if there was no uncertainty in what our actions were taking, then we can come up with a plan for what to do. If we're here, we can go up, up, left, left, or up, up, right, right, right. And we can reach the +1 and we can be happy, right? Like, that's the minimum cost path to the goal. And how could we compute this? What's one way to compute this trajectory? If we're in a deterministic world. Yeah.
Just use any sort of like breadth first.
Yeah, you can use, we're back in our uninformed search, or you could use any star search if you wanted. If you came up with a good heuristic, you could use any search algorithm you wanted to basically find this trajectory. But what's the problem with this in a non-deterministic world, in the world where some of our actions could not succeed? Yeah.
If you only go up, like if you initially go up, it says you go perpendicular to it, so you might,
Yeah.
do this, end up hitting the -1.
Yeah. So what happens if I go off script? So I try to go up, but I get unlucky, and I actually end up over here. Then my plan doesn't say anything about what I'm supposed to be doing. So we talked about this before with sort of the difference between a plan versus a policy. So the search algorithm is going to tell me a plan for where my current state is. What can I do to get to the goal state? Whereas a policy is going to tell me for any state that I'm in, what action sequence can I take to reach the goal. So it turns out if I put this non-deterministic action model in, the probability that this action sequence reaches the goal is 0.8 to the 5th, because I need every single action to go right in order for that to make it to the goal, which is something about a third, right? So with reasonably high probability, this will not take me where I want to go. That said, we're going to talk about how we can compute a policy with an exact algorithm. But what's a way to use our uninformed search, or whatever, our sort of traditional search methods, to get a policy? So, yeah.
Can you just redo your
Yeah.
uninformed search each time?
Yes, I could just run it again. So like I start going up, and then afterwards I rerun my uninformed search algorithm, and if I went off script, it's going to come up with another one that's different because I'm in a different start location, and just keep doing that over and over and over and over again. Yes?
So you do know where you end up.
You know where you end up. The difference between an MDP and a POMDP, a partially observable Markov decision process, is that you do not know where you end up. So after you take the action, you get to know what state you're in. So this idea of running your planner over and over again, people call it model predictive control, and they call it forward search. And it's actually a really powerful idea. It works really well. And there's a lot of theoretical work on when to do it and stuff. We'll sort of talk about at the end. We'll talk about other ways of approximating solutions. But the first thing we're going to talk about is sort of the way to do this optimally. So to actually find the policy. So this is a slide from before. We were talking about this with games. If you remember when we were talking about alpha beta pruning, we couldn't just come up with a sequence of moves that we were going to take because we didn't get to control the other guy's moves. It turned out that with alpha beta pruning that we could decide, well, even though we don't get to control them, we can infer something about them because we are assuming he wants the opposite of what we want in these adversarial games. So we could still just kind of search. So we were coming up with a policy, but we could kind of search through the policy tree with minimax or alpha beta pruning in a way that told us what to do in each state. Here it's a little different because we don't know, it's not deterministic, right? So there's this sort of chance element in the world. So what does the policy look like for this world? So don't tell me. Search just tell me like the form of what the policy is going to take. It's kind of like it's a function, right? So what's the input and what's the output of the function? I'm going to ask somebody else. Yeah.
The input might be like the state that we're currently at.
Yep. Good.
The output would be like the direction that it's most likely.
Right. Yes. So a policy, which people write as pi, because for policy, and the input is the state, and the output is an action for that state. So for each one of these grid cells, that's representing a different state that I could be in, and the output to be a policy is going to be an action. So what do you think, if I'm in this grid cell up here, what do you think the optimal policy is? What do you think the best thing I could do there is? Left, right, or up? Right, yeah. Yes. I should go this way. So what about this one? Right, yeah. So we can just kind of keep just using our intuitions and fill this in with this trajectory that goes to the goal. And that, question? Okay. So that's sort of one example policy for this domain. And it turns out to be the optimal one for the setting of the reward function in transition dynamics. If we change the reward function, is that a question?
Yeah.
Yeah.
So do we care about the number of steps it's taking? Because if you're in the one right before the +1,
Yep.
if you just always try to go up, it says, you can't go into a wall, so eventually you move to the right and you wouldn't have any risk of going the wrong way.
Yes, that's exactly what we're going to get to next. So this is the optimal policy for the reward function where all other states have a reward of minus 0.04. If we change that value, and that's exactly what we're going to do next, you'll see that it will become, if the world is so horrible that it's just rather end than try to get to the goal, then it'll do exactly what you're talking about. It'll try to hit the wall just to avoid, or well, there's a range basically where it'll try to hit the wall to minimize the chances of getting the -1 reward. If the world what would happen if the reward's positive over in other states? It would run away from the goal. Yeah, it would just never try to get to +1 or -1. It would just go forever and try to stay alive forever because it can get cookies as long as it avoids those termination states. So we'll sort of talk about this. So this is sort of what a policy looks like. People use pi to represent as the variable that represents the policy. It's a function that takes as input a state and outputs an action. So for any state, I can ask my policy what action I should take. And it'll tell me. And if it's the optimal policy, that means it's the one that gets me the most reward. So the next one we're going to talk about is sort of this whole idea of different reward functions. So here, our reward function, so what we're changing here is the reward for being, and these are always +1 and -1. We're changing the reward for being in any other state, basically. So in this world, instead of getting -0.04, it's getting -1.6284. So these numbers are from the book. This is sort of what there's different regions of policies that give you different reward functions. So what's going to happen in this world? It's like no matter what it does, it gets negative reward, a lot of negative reward. Yeah.
Not going to go anywhere.
Well, it has to go somewhere. So it's not allowed. So sometimes that does happen. So there was there's a domain that we would work with. It was called persistent search and track. And the idea is that you're supposed to send out these helicopters with limited battery life, and they're supposed to go out and observe the world. And if they see certain things, they get cookies. And every time step that they don't see things, they get a small negative reward. And if they crash, they get a huge negative reward, right? Because it's bad if your robot dies. And for a lot of, and then the problem with this domain is that the base space was really big. So if you used a naive algorithm, the best policy it could find was to stay at base, because at least you wouldn't crash. Like they couldn't guarantee that you'd actually get to a earning reward, so it would stay home and crash. In this world, we're not allowed to do that. So it could be that we could stay, huddled in our square, but we define the domain that you have to go somewhere. But you're close in terms of what the right policy would be. So given that we have to go somewhere, what should we try to do? Yeah.
Go to the closest guy. So like given the option of -1,
Yeah.
like immediately in +1 with a few moves, it'll just go to -1.
Exactly. Yeah. So it's so terrible that I don't even care. I'm not even going to try to go to the +1 place. I'm just going to try to get out of this world as fast as I can. Right. So it's just going to run for the exit, and it doesn't matter if it's +1 or -1. It's not even going to care. So now let's look at a range where the reward is not as good as it was before, where it was 0.04, but it's not quite so horrible. So what are we going to do here? Yeah.
What's the method by which those policies are computed?
So what? What's the method by which these are computed? You can work out the math of where where the policies basically change. And we'll talk about that next when we talk about the values of different states. So it turns out, so what we're trying to do, I think maybe I put this equation later, but what we're trying to do when we come up with these policies, so maybe I should have moved these equations around. What we're trying to do when we come up with these policies, and I'll talk about value iteration, which is one way to compute these policies, is we're trying to maximize our reward, our expected reward, right? Because we can't maximize our actual reward because it's non-deterministic. We're trying to maximize our expected reward. And it turns out that in this state, because my reward for just living is so terrible, the way to maximize my expected reward is to just dive for the home base.
And so the
Yeah.
calculation is just something you're talking about.
What's that? Yes, it kind of falls from summing the reward over each time step and marginalizing over the different states that I could come. And we'll actually go through this math next. Okay, but that's and these ranges come from doing that. Where these different ranges fall is based on the details of the transition dynamics and the reward function when you work out those expectations. Yeah.
So when you're calculating where to go next, are you
Yeah.
not taking into account your expected policies, a few moves, or expected reward of a few moves ahead?
So these policies are optimal for these reward functions. And right now, what I was trying to do is just kind of give the intuition that different reward functions, different specifications for the problem can give you different policies, right? So in some worlds, it's better to go to -1 as fast as you can. In other worlds, it's not, without actually getting into the nuts and bolts of how we get these policies. What we're going to do after this is that. So and the way that we'll do it is by computing our expected value of being in each state in an iterative way. And that's what value iteration is. Okay? Okay. So basically what I wanted to do here was kind of give the intuition that there are different policies that could come out. It's not obvious what the answer is in advance. You sort of have to work out the relative value, the relative cost of being alive versus the rewards of ending in different spaces. So like for this one, it's going to try to go to the +1 here. So it's not so terrible as all that, but it's still going to go next. So what's significant about this one, this decision right here to go up here? What could happen in this state? It could end up in -1. So why doesn't it decide? So it went all the way around here, right? It would have a smaller chance of that happening. Why doesn't it decide to do that for these two states?
Yes, it's the cost of doing all that.
Right. So with this range of the cost of being alive, it's really not worth it for it to try to take the long cut. It takes the shortcut, even though that might end up getting -1 reward, because the cost of just doing all these steps is so high. So when you work out the expectations and the probabilities and stuff, this turns out to be the right thing to do. So here the reward is even smaller. So what do you think this one's going to do? The cost of being alive is even smaller.
If it's small enough, it'll be happy with going all the way back around.
Right. So it's going to be so what we were talking about before. It's going to be super conservative, right? So it's going to decide here. It's going to try to hit the wall because it's rather get here or here than have any risk of getting -1 reward. The expected value of hitting the wall is better than the risk of hitting the -1 when your cost of being alive is that small. Does that make sense to everybody? How this is sort of changing the different reward functions that are leading to very different policies, even in this very simple world. So now, what happens if we have positive reward for being alive? We talked about this one before, right? We're gonna just try to stay alive forever. So what is that going to mean for these states? Yeah, head away from the goal. So as long as you try to avoid those goals, it doesn't matter what you do in these other states. Since we can never go backwards, we can just guarantee that we're going to get out of these states. What if we could go backwards? So if there was some chance that we would end up backwards in the goal, would these states matter then? Yeah, they would. So because we can never go backwards, these states are a really good gate. So anything in here, it just doesn't matter because these states are always going to protect you. If there was some chance of slipping into the goal, then they would try to keep you, like let's say there was some chance of going backwards, it would try to keep you as far away, I don't know, like maybe here, as possible. And it would be driving you there to minimize the chance of slipping, and ending up in one of the terminal states and stopping your good thing that you got going here, where you get lots of cookies for being alive for a long time. Okay. So finding the optimal policy, maybe I should have talked about this first instead of second, but I don't know. I just hope to get the intuition of it first. So the first thing we have to talk about is what does it mean for there to be a utility? So what does it mean to earn maximum reward over time? So there's a couple of ways to define this. So what's one way you guys can think of? This isn't a trick question. Like if you're taking lots of actions and you get reward, what's one way to compute the reward for a state sequence? Yeah.
You just add up the rewards.
Yeah, you just add them up. So you're just going to say if I have the state sequence of S0 to Sn, I'm just going to sum them up. So what do you guys think about that? Seems good. What does anybody get a little nervous about this? Yeah?
Well, when you're thinking about like your policy, you don't take into account that maybe you're not going to end up with the state sequence you want.
So we'll talk about that. So what we can do is take what we're going to be doing is taking the expectation on our utility function. And we can take the expectation on this. So this is saying, given that we know for sure, so the expectation is going to come later, given that we know for sure what our state sequence is, this is one way to compute the utility of being in that state, how good it is to be in that state.
One issue that you might have for certain problems is you might have a reason that you prefer, you care more about stuff that happens at the beginning or stuff that happens at the end.
Exactly.
Use,
Yeah.
You know, R of S0 plus R of S1 squared plus R of S1 cubed or something like that to weight one end or the other.
Exactly. So
Why would you not just factor that into your reward function then?
because it might be relative. So it might be relative to. You want it to be the same no matter where you start out. You want so your reward function. This is the whole idea of Markov, right? So we could have a non-Markov version of this where it depends on our history, for example, whether I'm at the beginning of the state sequence or at the end of the state sequence. But if I want to define it in a Markov way, then my reward function can't depend on the history. So I have to do something else to make it depend on time. And in particular, so this is called additive rewards. I'm just going to sum them all up, and that's what I'm going to try to optimize. Another thing that people do is discounted rewards. So this is basically what you were saying, only you have this gamma that you're raising to the power. Gamma is some number less than 1. So what's this going to do in words? You have your hand raised? You? No? Okay. All right. Yeah.
Oh, it's going to weight the earlier ones more than the later ones.
Yes, exactly. So it's going to say the reward that I can get now is better. A bird in the hand is worth two in the bush, right? So the reward I can get now is worth more than the reward that I can get later. And this turns out to be a pretty nice way to formulate the utility, especially when this is not finite. So in our grid world that we were working in, these states terminate the whole thing. So we always know that our sum is finite, and we can actually optimize it. In a lot of our MDPs and POMDPs, there is no terminal state. So what's going to happen with our additive reward? What could happen? Yeah.
It goes to positive or negative infinity.
Yeah, it could go to positive or negative infinity. And maybe we know that positive infinity is better than negative infinity, but it doesn't let us wait between, infinity is infinity. So there might be one that kind of seems like it would earn more reward, and the one that seems like let's say that there was a terminal state for +1 and +2, right? Like you kind of want it to, as a designer looking at this problem, you'd want it to prefer going to +1. Like let's say there was not a terminal state, but a really good place to be where you could get +1, another really good place to be where you get +2 over and over and over. If you're using additive rewards, it won't care. Like if it's just going to both be infinity, and infinity is you can't compare two infinities, so it's not going to have that preference. And maybe that's what you want, but so often it's not. And the advantage of this discounted reward is that it will care about that. So because you're discounting the future, this will converge, and it'll prefer the +2 state over the +1 state. Okay. So basically, this makes the math work out nicer, because you don't have to deal with infinities. Okay, so this is back to your question. What do we do to actually find the optimal policy? We'll take expectations over these utility functions. So here, summation, the expected value over the reward that I'll get by executing the policy pi, right? So I'm going to, for any policy that I have, I can compute the expected reward, the expected utility of being in that state and just playing out the world. I mean, you can think of it as this summation is going to be over all the state sequences that I could get by executing that policy. So it's going to be an infinite summation, but it turns out that so this is the finite version, this is the discounted version. It turns out that it converges because even in infinite spaces with the discount factor, I can actually get a number for this expectation, and which people call this function is called the value function. Why it's called value iteration, and I can search for the policy that maximizes the expected utility. Okay, so that's what it means to be a good policy. So how can I actually compute this? So the way so we're sort of saying you can sum over all the possible state sequences, but it turns out that this collapses in a really nice way. So what you can do is say the utility of state S. That means people sometimes, in the book they call it utility, in other literature they call it the value of being in state S. The expected return of being in state S and executing policy pi from here on out. I can write this recursively. So it's got two parts. The first part is the reward for that state. Okay, so this is just, I get a cookie for wherever I am right now. And the second part is the future. So I'm going to take an action, and here the max is I'm going to take the action with the best utility. I'm going to define it in terms of itself. That is most likely to take me to the S prime with the highest utility. So I'm going to pick the action that moves me with the most probability moves me to the state with the highest expected utility. That's what this says. And this equation, this sort of recurrence relation, is called the Bellman equation, and that's what is going to underlie our value iteration algorithm. So what you can do is, if you have an estimate for the utility that might not be very good, you can use this to make a new update and a belief not a belief update, but like an update based on what by sort of backward propagating the utility through your estimate and come up with a better and better estimate of the true utility, true value function. And then if you know the value function, then you can use that to get a policy by always moving to the state that maximizes your expected value. Does that make sense? There's kind of two steps to the way the algorithm works. And this equation is sort of underlying a lot of the, it's also going to underlie the RL stuff that we're talking about, this idea that there's this recurrence in the way that you can structure MDPs and POMDPs. So we're going to do a historical aside now. This algorithm value iteration, and there's a family, is called dynamic programming. Does anybody know why? Who's heard of dynamic programming? Yeah. So I had heard of it too when I took an algorithms course, and you learn about these different dynamic programming algorithms where you're saving things up in a big table and computing them based on their neighbors, right? It's this sort of particular way of programming. And it turns out that the word dynamic programming was coined by Bellman to solve MDPs. And this is what he wrote about why it was called that. So he said he felt he had to do something. So he was a researcher that was in an industry research lab, that's Wilson, funded by the Air Force, but at the time the government was very against mathematics and mathematical research. So he needed to have a name. So he had to do something to shield Wilson in the Air Force from the fact that I was really doing mathematics inside the RAND Corporation. What title, what name could I choose? So in the first place, I was interested in planning and decision making and thinking, but planning isn't a good word for various reasons, so there was like bias against that word. So he decided to use the word programming because he thought that sounded better. I wanted to get across the idea that this was dynamic, this was multi-stage, this was time varying. So he said, let's kill two birds with one stone. Let's take a word that has an absolutely precise meaning, namely dynamic, in the classical physical sense. It also has the very interesting property as an adjective in that it's impossible to use the word dynamic in a pejorative sense. So he said, try thinking of some combination that will possibly give it a pejorative meaning. It's impossible. Thus, I thought dynamic programming was a good name. It was something not even a congressman could object to. Thus, I used it as an umbrella for my activities. So that's why we have dynamic programming as the name for these algorithms. I thought it was pretty funny when I first realized. Not only that people called this dynamic programming, and I didn't realize that this was where the idea was invented, and then they went on to be applied to these other related types of algorithms. But also that the reason he chose it was so, I don't know, mercenary. It sounded so mathematical when I don't know what you guys thought when you first came to it, but I was like, oh, it sounds very hard and complicated and exciting. So anyway, these algorithms, value iteration, policy iteration, this is where these algorithms were, why the word, this is the original dynamic programming algorithms, and then the idea went on to other parts of computer science from here. And basically what you're going to do in this algorithm is you have an estimate for the value function, these vectors of utilities. So what they're going to do is take in a state. It's a function, even though when we code it up, we're going to represent it as a matrix, right? So it's going to take as input a state and output a real number that tells you the expected discounted reward for being in that state and executing the optimal policy afterwards. So the way that it's going to do this is for each state S, it's going to take its old estimate of the utility and then compute the reward of being in that state plus the expected utility of the successor state. So it's going to come up with the best action. This is going to be maximizing over all the actions that you could take, and then basically do this update. And then so what this check is doing, what is this doing? Anybody want to say what this line's doing?
I'm just looking at the difference in the reward of your
Yeah.
state and your possible next state.
It's looking at the difference in not the reward, but the utility. So what's U prime and what's U?
It's just the overall utility of being in this other state or being in your current state.
So S prime is another state, and S is my current state. What's U prime and U? So every cycle, U gets to be U prime, and then we're updating U prime, right? So the high level flow of the algorithm is doing what?
Is it the utility of the same state in the new iteration?
Yeah, so we're iteratively estimating the utility function, the true utility function. And U prime is my next estimate, and U is my current estimate, okay? So here what we're doing is we're using our current estimate in this update. So we're using the current estimate to compute the best action and the reward of that, the value of that, and then we're using that to make a new estimate. So the sort of high-level flow of the algorithm is every time we take a U, we use it to get a better U. And our U prime is our better U. And then at the end, where do we do that? We make U equals U prime, and then do it again. And we just keep doing that until it converges. So what is this check doing?
That is still changing and it's not gonna break.
Yeah, it's going to check that it's still changing. So delta is just saying, I think it says here, the maximum change in utility of any state in an iteration. So I'm just going to keep going until things stop changing, okay? And then hope that takes me to a good place. And if you read the book and the research literature, you can prove that this actually does converge. So it will eventually stop changing too much, and it'll converge to the true utility function. And once you have that, you can use that to come up with a policy. Does that make sense to everybody? Yeah.
What's sigma?
What's sigma?
Check until.
This one? Delta.
Oh no, but what's the first letter?
This is a delta.
No, in front of the parenthesis. Oh,
Epsilon.
it's epsilon. What is that?
The maximum error allowed in
Oh, okay.
utility.
Sorry,
So
that's
it's
it.
basically saying how big a change you're allowed to make, and they're scaling it by gamma. So
Sorry, I was
depending on
trying
how
to
far you're
get sigma
discounting.
too. One of the up there
Yeah.
looks like a T. Down there.
Yeah. Okay, so does that kind of make sense to everybody? We're going to go through an example, and then we're going to code it up. Okay, so so here's an example in the corridor problem. So basically, it's like a grid world, only it's linear. There's only one dimension. Your goal is to get here. You can go east and you can go west. So this is a really long-winded way of saying that if you go east with 0.9, it's going to send you east, and with 0.1, it's going to send you west, and you're not going to stay where you are. And these numbers are sort of, so I can say that in words really succinctly. These numbers are actually how these algorithms typically represent a transition matrix. So they'll actually roll out the whole thing explicitly like this. And a lot of these updates can actually be expressed as matrix operations. This is important to understand because it gets at the intuition of why these, like even though they're optimal, these algorithms we're talking about are optimal, it's why they're slow, right? Because we're going to roll out everything explicitly. We're going to exhaustively enumerate the state space, and we're going to do it every single time. So when we do this update here, we're actually going to iterate through every single state in the whole thing, not just the current state that we're in. We're not really in a state. We're going to do every single state in the whole thing, and then every single action we could take in that state. And we're going to do that in the inner loop of our thing, right? So we might have to run this update, 100 or 1,000 times to get to convergence, and that's in the inner loop of what we're doing. So, okay, and then a reward function. So we get +1 or +10 for being in state 3, no matter what action we take, and -1 otherwise. So here I did it with a reward function for a state and an action. So we'll sort of see how that works in the other way. So because we're in this reward function with a state and the action, we're going to estimate our U. We're going to change the letter to be Q, and it's going to be the utility of being in a certain state and taking an action. And then we're going to use this to compute the value function. Okay. So how do we get our Q? So how do we get this number? So here it's broken out into the actual numbers, but I didn't put the equation on the screen. So what's this -1 coming from? Exactly, yeah. This is the current reward for being in state 1 and executing east. So I just looked up in my reward function for what that was and plugged it in here. What's the 0.1? What symbol does that correspond to? The gamma, my discount factor. Yeah, yeah. Got to get better at our Greek letters. All right, and then what's 0.1 times 0 plus 0.9 times 0? Yeah.
Iteration over all the other states times each of the.
Yeah, so this is where I could end up in response for that. And then I'm looking up the value of that state. So my initial estimate is 0, so these are all 0. So this all goes away, but I did it explicitly so you can see how the update happens the first time. So then we compute all that. It's basically working out to be the reward. And then we can go from this to the value function by doing our max operator. So how does that work? It's actually kind of a no up everywhere, right? So I'm basically going to max over, for state 1, I'm going to take the value of the maximum action. And it's always -1, and it's -1, it's 10, it's 10. So it doesn't actually even matter. Okay? So now we're going to do it again. So this is our first iteration. And our value function is kind of just replaying the reward function. It doesn't really tell us what the right policy should be. So let's do another iteration. Okay? So this is sort of playing out the whole thing over again. So what's this first column, these first numbers? Same as before. The reward, yeah, the reward for being in that state. And this is discount factor. So what is these 0.1s times -1 plus 0.9 times -1? So if I'm in state 1 and I take the east action, I could go to state 2, or I could stay where I am, right? So if I hit the wall, I stay where I am. So what I'm going to do is, and that's 0.1 and that's 0.9, that those two things happen. I'm going to go and look up in my value function and see, oh, this is the value of this is -1, and the value of this is also -1. So I get an update like that. So things get interesting in state 2. Okay. So what happens in state 2 when I do that? And I take the east action. Yeah, I get a really big a really big reward here if I take the east action versus the west action. What happens? My 10 is multiplied by 0.1, right? So if I play this out in state 2, what's it saying is better, east or west? East. Yeah, it's negative. So right. So the biggest number here is the one that is encoding the optimal action. So I still don't know what to do about state 1. This is after the first iteration of the algorithm. But what do you think is going to happen the next, so then I can sort of update my value function with that. What do you think is going to happen the third time I go through? What's that? For state 1. Yeah, it's going to figure out that I should go east for state 1. So that's how the information kind of propagates backwards at each iteration. It's kind of moving back one state at a time towards the start state. It's kind of like a backwards chaining E kind of way of thinking about it. Like it's flowing back through the graph. So after my first iteration, I didn't know what to do in state 2 or state 1. Now I know what to do in state 2, but I still don't know what to do in state 1. But eventually, I'll converge. This is also bringing out an interesting feature of these algorithms. It's a trade-off we'll be talking about a lot in reinforcement learning and MDPs and all this stuff. So we're doing all this work to come up with this value function. Do we have to do all that work? Just intuitively, like, do we really need to know these values or not in order to act optimally? Yeah.
I guess you don't need to know exactly what the value is, you just need to know the relative order.
Exactly. So value iteration is actually going to compute the value function or the utility function, the expected discounted reward from being in a particular state. And it's some number, like we can actually estimate what that is. And if we have that number, we can compute the optimal policy. But if our goal is only to act optimally, then all we need to do is compute the policy. And that's it. And the policy might be a lot simpler than actually assigning these real numbers, right? So the policy, the number of different policies that we could have is much smaller than the number of different value functions we could have, right? Like, so I can just enumerate, I can give you a finite list of all the policies there are in this domain. It might be big, but it's finite. Whereas the number of value functions is infinite, because each one is a continuous number. So sort of intuitively, there's reasons to think that you might do a lot better by just estimating the policy. And we'll talk about algorithms like that that are based around that intuition. There isn't really consensus in the literature about this. So this is sort of related to our machine learning questions, where you could do generative, you could do discriminative, or you could just directly estimate a decision function. And I think in machine learning, there's like more consensus about the different trade-offs of these approaches and how it affects you. And reinforcement learning is younger, and people don't really have, like, we can sort of say intuitively, yeah, maybe it's harder to estimate the value function, but there's, I don't know, that people are still kind of not clear on what the difference between these different approaches is. Okay, so that was sort of doing it on slides. So now we'll do it in code. And maybe, since we're kind of running out of time, I will just show you the code instead of coding it up from scratch, because I want to get to MDPs too. So let me make it bigger. Okay, so basically what I have is a definition of the same grid problem that we were working on before from the textbook. This one, coded up in Python. So you have the goal cells and the walls just encoded as grids, and then there's a transition model that tells you for being in a particular state 1 and state 2. These are the different probabilities, point 8 and point 1 of having the outcome be that particular outcome. So when we do this, we can code up value iteration, and the code pretty much corresponds to the pseudocode we were looking at before. So for each, so UP is U is the utility, U prime is the updated estimate of the utility. And at each step, I coded it as a generator, so it's going to yield the current estimate, which starts out as 0, and then it's going to do this update, the same kind of update we're doing every time. So here it's going to get the best over all the actions. It's going to compute the sum using U and the transition matrix. Yes?
What is yield?
Yield is a Python thing. So what it says is every time it's like a closure. So every time I call so basically what I'll do is show you where I call it value iteration. So I'm going to call it like this for U in value iteration, and it's every time I call yield, I'm going to get back a U, and then I call it again and get back another U. So that way I can do it in one loop, but what we'll do when we run it is plot it up on Matplotlib, so you can see what it looks like after every iteration.
Sort of return it like an iterator.
Yeah, it is an iterator. It's the way you make your own iterator. So I could, so that's, sorry for if that's too weird of a Python construct. It is kind of nice though, because it lets you code it in a very nice way. Otherwise I would have had to pass the U back in and do the update with some more bookkeeping. Here it's a closure, so I just get to keep going. All right, so I get my max result, I do my update. So here I look up the reward of being in the current state, and I multiply by my discount factor and the summation, and then here's my check if I've converged. So if things are too different from, once things stop converging, it's going to exit. So when we run it, see how this looks. It's kind of hard to see, but these are all zeros. This is the goal state. This is the +1 state. This is the -1 state. Here. So every time I hit enter, it's going to do a new update. So here, it's basically, this is the -0.04 cost of being alive, and the +1 and the -1. And then just like before, these rewards are going to feed back through the system. So here, it hasn't changed too much, but this plus 0.75 kind of propagates back through and tells us what to do, and eventually we get back to the start state. And if we keep running for a while, it's going to converge. It basically, it doesn't actually time out from the if statement, but you can see that these numbers stop changing. I'm getting a better and better estimate of the utility, and you can see that you can use this matrix to look up a policy, the right policy. And if I change the reward function, so to some of those other reward functions we were using earlier in class, you would get different policies. And you could either run through all the different ranges of reward functions and just find where the policies shift. And that might be like the hacker way to do it, or you could do math to actually figure out where the policy shifts. Yeah?
So right now you're just storing the size of the value function, but if you wanted to do a policy, you could easily just have another vector.
Yeah, so what I would do to get to a policy is, if I was in this state, let's say, I would find the expected utility of taking action left in this state. And I could do that by multiplying by the probability of being in that state and looking up the utility in the other states. And I would maximize my expected utility. I'd pick the action that maximizes my expected utility. So it's confusing because people talk, I would get confused about this because people would talk, oh, I have the value function and now I have a policy. And what they mean is, it's once you have the value function, there's another algorithm you can run that is pretty fast to actually get the policy. But it's not the same as, but that versus policy-based methods is you're directly estimating the policy. So I'm just, I could imagine like this sort of, the first thing you might try to do that is just enumerate all the policies, try them, run them 100 times or 1,000 times, compute the return, and then pick the one that gets the highest return. And that might be really slow, but you wouldn't actually have to estimate the value function to do that. And there's other ways to do it that are faster. Okay. All right, so let's zip back to value iteration. Okay, so this is sort of summarizing. So VI, value iteration, is sort of the, I don't know, it's almost like, it's like breadth first search for MDPs. It's like the canonical way of solving them. It solves it exactly. It might take a long time to converge, but you're going to get the best policy. The problem is that we had to enumerate all the states and all the actions. So we're sort of alluded to these policy-based methods that help you avoid that. There's also feature-based methods. So just like in machine learning, where we came up with these feature vectors and then we learned feature weights to make a decision function, you can use linear function approximation-based methods to estimate your value function. And what that will let you do is generalize across different states. So you might not, if you're doing these feature-based methods, you can sort of learn that it's a bad idea to be near that -1 reward state. Like it tends not to work. And so without sort of intuitively, if we go back to our grid world problem, intuitively, like this state and this state are kind of related to each other. They're both right next to this -1 chasm state, but when we're doing it with brute force, we're completely separately estimating the what to do here versus what to do here. With these feature-based methods, you might have a feature like, well, I'm kind of close to the -1 state, and that would learn that it's good to go away from it in a way that's more general. And then people do this also. So another way of breaking down the states is with propositional methods. So there's a paper that Michael Littman here wrote about object-oriented MDPs, where you can basically factor the state space in a different way, and it also gives you a speed up. And then we already talked about policy search-based methods. I'm going to skip this because we're almost out of time. And we're going to talk in the last couple of minutes about partially observable Markov decision processes. So somebody at the beginning already sort of asked about this. So in MDP, this is an MDP. We know the states, the actions, the transition dynamics, and the reward function. So what happens if we don't get to know what state that we're in? What does that mean for our little robot?
We have to go to the best thing no matter where we are.
Yeah, we have to, we kind of have to estimate where we think we are and then do the best thing no matter where we are, taking into account that we might have no idea what state we're in right now. So people formalize this by giving our little agent access to observations of the environment. So an observation function, so I have the set of all possible observations. An observation function takes as input a state and an action. It gives me, it takes an input a state, an action, and an observation, and tells me the probability of seeing that observation given that I'm in a current state and a current action. So it's a distribution over, so I can use this to estimate, given an observation, using Bayesian, I can flip this around and use this to give me a distribution over states given a particular observation. So what does this remind you of? This idea of like I'm observing, I'm a current state, I have some probability of seeing one detector fire or another detector fire, and that's different for different states. What does that kind of feel like? Particle filter. Yeah, it's like our Bayes filter. It's actually exactly like our Bayes filter. We can do this and sort of over time come up with a distribution over the states that we're in. So what was missing when we were doing our particle filter problem? What was missing? Like what did we explicitly decide not to think about? If you remember the Bayes filter. I think I have it up in a future slide. What did we not think about here? What were we given and we didn't get to decide? Yeah.
Or I mean, we don't think about our history beyond one state.
That's true. That's true. But we're still not going to think about it. We're going to summarize our history. So just like before, we're going to maintain a belief over our state. And that's going to summarize all of our previous history, right? So we're not going to we're not going to remember the specific sequence of histories. We're just going to maintain this estimate. Yeah?
You're not giving the input?
The control input, exactly. So we were given, in our Bayes filter, we were given the control input. We didn't get to pick what it should be. In our POMDP, this corresponds to the action space. So we get to pick the action that maximizes our expected return. And as we pick our actions, we're going to estimate our belief, and that is what we're going to use to pick future actions. Okay, so this is sort of our robot, our complete model of our robot. We're going to estimate how we think the world, what we think the world looks like, then we're going to pick actions based on that estimate that maximize our expected return. Okay, so we'll sort of go through an example. So this is sort of the canonical POMDP problem. It's called the tiger problem. So you're a little guy, and there's two doors, and behind one door is a tiger, and behind the other door is nothing. You just get to stay alive. And if you open the door with the tiger, you get a very large negative reward because there's a tiger. There's a tiger. And if you open the other door, you get a small positive reward because you didn't get the tiger. So the state is there's a tiger behind door 1 and there's a tiger behind door 2. So if you knew the state, what would the best action be? Yeah, don't bother the tiger. But we don't know the state. So instead what we have, so we can, is the ability to listen and get an observation. So if we listen, then this is sort of depending on the two states. So there's more rows to this that I didn't write down. If the tiger's behind the left door, we're gonna get the observation that the tiger's behind the left door with probability 0.85. And the probability that it's behind the right door with 0.15. And if it was really behind the right door, it would be the other way around. So we can choose to listen, and if we don't listen, then we get 0.5. We get either observation with 0.5. We don't get additional information about where the tiger is. So what do you think you should do in this POMDP? Yeah?
Continue listening as long as you possibly can.
Well, should you do it forever, or will you eventually stop?
So if you keep listening, does your probability actually increase? Like, do you get to multiply that 0.5, or do you always hear the
Yeah.
same thing? Oh, then you should do it until eventually the expectability is greater than expected.
Exactly. So what you're going to do is run a Bayes filter, basically. You're going to listen, and every time you get an observation, you're going to update your belief over where you think the tiger is. And eventually, if things really follow these dynamics, it's going to converge. It's going to be smaller than a threshold in terms of where the tiger is. I actually should have put a negative reward for staying alive. Otherwise, it might just listen forever. And then it's going to decide, okay, well, I'm really sure the tiger is here and not here, so I'm going to just open the door and hope things are right. Yeah.
The probability that it's behind the left or the right door is not known
this is known to when you solve a POM-DP, this is known. So you get to listen and you get to know the sort of true dynamics. And the thing, so I guess the point I wanted to make is that like for these, so what you are estimating is your different belief states. And depending on where you think the tiger is, so this is just saying, do I think the tiger is left or do I think the tiger is right? I'm going to have a different optimal action. So if it's between 0.10 and 0.9, I'm going to listen. If I'm sure 0.9 to 1 it's right, or I'm sure it's left 0 to 0.1, my optimal action, if I work out the expected reward of taking that action, is to go left or go right. And this is sort of a graph version of the policy. So this is basically counting up how many times I have to hear it in order to actually take an action. So like every time I hear it right or left, I'm going to go here, and then I'm going to open the right door. Right, so this is sort of a graph version. But what this is the exact same math as I said before as the Bayes filter, except we get to choose the actions now. So I'm going to sort of, this is the belief update. We did almost the same version of this with the Bayes filter when we flipped our variables around and did an estimate. So we were writing our updated belief in terms of our previous belief, the transition dynamics, and the observation function. And this is basically using Bayes' rule and then making some independence assumptions that let us plug in the stuff we get directly from the POM-DP. So the thing to take away is that POM-DPs are a lot harder than MDPs because they're continuous. But actually, if we switch to the belief state, we can make it back into an MDP in the belief state. So we have this, our new state space is the set of belief states, and then we have a transition dynamic for updating our belief based on the action that we take. Not our state, but our belief over the state. And then we get reward for believing, just for believing that we're in a good state. We get reward. And that might seem weird, but it's actually correct because we're being Bayesians, we're following Jaynes. And so our belief is actually correctly modeling the true dynamics of the world. So this relation between MDPs and POM-DPs. Okay, so that's it. We talked about MDPs and POM-DPs. In next class, we're going to talk about reinforcement learning when you don't know the transition dynamics. Thanks, guys.